Calculus Unit 5. This is Day 41 Notes, Part 3. Um, so we have another problem here. So the total order and transportation cost, C of x, measured in dollars, of bottles of Pepsi Cola is approximated by the function C of x equals 10,000 times the quantity 1 over x over x plus 3. Where x is the order size in number of bottles of Pepsi Cola in hundreds, answer the following questions. So I see down in part B that I have to take the derivative. So I'm just going to take time right now just to rewrite the C of x so it's as one fraction. So what do I need to do? I need to get a common denominator in here. So this part's going to have to be multiplied by x plus 3 over x plus 3. Sorry about that. Second one's going to be multiplied by x over x. So this is going to still be 10,000 times x plus 3 plus x squared all over that common denominator x times x plus 3. And let me just write it so it's in standard form. 10,000 x squared plus x plus 3 all over x times x plus 3. Again, I just saw that dealing with the derivative down there, so I'm eventually going to have to take the derivative. Um, and so let's look at part A. Is there guaranteed a value of r on the interval from 0 to 3, when r is between 0 and 3, such that the average rate of change of cost is equal to c prime of r? Give a reason for your answer. Okay, well, that's going to be dealing with the mean value theorem. And what has to be true is it has to be continuous, it has to be differentiable, and so I see that I can take the derivative, that's good. Um, and then I would have to, the slope of the tangent line is going to have to be slope of the secant line, but let's check to see if it's continuous. Well, as I look here, um, I find out that, hey, it's going to be undefined where the denominator equals 0, and the denominator is going to equal 0 um, when x equals 0 and when x equals uh, negative 3. Well, negative 3 is not on the interval, but 0 is on the interval. So I now know, since the function c of x is undefined at x equals 0, therefore it's not continuous on the closed interval from 0 to 3, therefore the mean value theorem does not guarantee a value of r on that interval. So let's write that out. So again, since the function is undefined at x equals 0, and how did I do that? I found out where the original function, again, to be undefined is when the denominator equals 0. So I looked at when does x times x plus 3 equal 0, and I know x equals 0 or x plus 3 equals 0. One of those factors has to equal 0. And again, I get 0 and negative 3, but it's over this interval, so the negative 3, I'm not worried about that. Still undefined there, but it's not on our interval. But it's undefined at 0. So since it's undefined there, then it's not continuous. Therefore, the mean value theorem does not guarantee a value of r on the interval such that the derivative equals um, the slope formula. So again, the slope of the tangent line doesn't equal the slope of the secant line. All right, so let's look at the next part. So is there a value of r on the interval from 3 to 6 such that the derivative equals 0? And give a reason for your answer. And if such a value of r exists, then find that value of r. So now we're going to need to take the derivative. First of all, I know it's continuous, and I know it's differentiable. Um, and I'm really looking to see uh, if Rolle's theorem applies here. So I know it's continuous, I know it's differentiable. Let's just check to see what the values of the endpoints of the interval on the original function are. If they're equal, then I can use Rolle's theorem. Okay, so I'm trying to check, again, we said it's continuous on the closed interval from 3 to 6 and differentiable on the open interval from 3 to 6. I'm trying to check to see, again, Rolle's theorem says that the value of these endpoints must be equal. Well, I've already gone in and typed in some information in my calculator. So let's take a look at this. So when I go here, can I have the whole function 10,000 times x squared plus x plus 3 all over, and I just wrote x times x plus 3 is x squared plus 3x. Now I'm going to go into table set, start at 0, go up by 1, and now I'm going to go to my table, and hey, x equals 3, the value of the function is 8,333.3, and then when I go down to 6, it's 8,333.3. So, and that's actually a little rounding because it's 0.3 repeating. So what does that tell me? That tells me that Rolle's theorem is going to guarantee me that some derivative is going to equal 0. Um, and let's take a look at that. 8,333.3. And again, we said it's repeating. That's not a big deal. So then Rolle's theorem guarantees a value of r over that interval. Guarantees a value of r on the open interval from 3 to 6 such that c prime of r equals 0. Okay? And now that's what we're going to look for. And let's take the derivative, and because I'm going to use the calculator on this one. Let's take the derivative. Let me get a different color here. Oh, big product rule. I'm going to skip to the answer here. No, I could do it out. Um, so 10,000. So what do we got to do? Quotient rule. Hody high. So x squared plus 3x times the derivative of the numerator. That was ho was low, and then the derivative of the numerator is 2x plus 1. I'm going to have to give myself a little more space. And then minus the numerator, x squared plus x plus 3, all times the derivative of the denominator, 2x plus 3. Now I can put my numerator down there. All over the denominator squared. X squared plus 3x all squared. Now, I could go and set this equal to 0 and solve for it. That's a lot of work. So we're going to punch that into our calculator, and we're going to find out on the interval from 3 to 6 where this equals 0. Okay, so I've typed in the derivative. Again, you get 10,000. I'm just going to go through and show you. So it can get tricky here. So x squared plus 3x times 2x plus 1 minus 2x plus 3 times x squared plus x plus 3. And then that whole numerator was in parentheses. And then divided by, and then put the whole numerator in the, denominator into parentheses and square it. Okay? So now I'm going to graph this. Now I'm going to show you, I changed the window. I don't need to look at it a big spot. I know I'm just looking for the 0. And I went on the interval from 3 to 6. And I'm also going to just go from -5 to 5 because I don't need that far up and that far down. So we graph it. Here's my graph. And now I'm going to calculate the 0, choice 2. And left bound, you might have to move your cursor. Mine just happened to be right there. Again, you got to kind of look. And I know from my graph that it was kind of going up from left to right, so I should go a little bit left until I get in the negative area. Then I can hit enter. And that may be where you have to make a bigger window just to see what the graph looks like. And then I just need to be a little bit to the right of the 0. Enter. Guess. It doesn't really matter. Hey, 4.098. And I got to just go to 3 decimal places. So now, after graphing the derivative on the interval from 3 to 6, the derivative equals 0 when r equals 4.098. Okay? Good problem. All right, and let's just look at this last little part for x is um, x is between 3 and 9. What is the greatest cost um, for order and transportation? So we just talked about, let's that. Hold on. All right, so part C again from X being from 3 to 9, what is the greatest cost for order and transportation? So um, one of the things I know absolute max, absolute min are always going to occur at either the endpoints or when the derivative is at one of the critical points. So when and the derivative being 0 is one of them. Now I don't know if I made a mistake and that was supposed to be from 3 to 6, but let's just say it's supposed to be from 3 to 9. So I'm going to quickly go back and look at my graph. I know my endpoints, and I can find the value of the function when x is 3. Actually, I know that. We already did that one. That's 8,333.33. I can go back and find what the value of the function is at 9 because I still have that function. And what I said was I want to go, let's go back here. And what I did, when I go to y equals, I still have the derivative in y2. I just changed the window now from 3 to 9, and I even opened the y values. The key I'm looking for here is, though, that's only 1 0 between 3 and 9. So still that same value I found from 3 to 6 is going to be the value. So 4.098 is going to be a critical value. And I got to find out what the cost is at 4.098. I know the cost at 3, so let's go back to my calculator. I need to find the cost. So table set 0 by 1. So let's go to the table. Oh, I'm on y2. I got to go back to y1. Sorry. Um, and I can shut off y2. So now I want to find the table. Um, and again, there's my 3, 8,333.3, but I knew that up in part B, the beginning of part B. Now so that's when x is 9. I know the value of the function is 8,611. Let me just see what the decimals are. We should be going to 3 decimals each time. So now this is 8,611.111. And now I just need to do one more. I need to check when the derivative equals 0. Is that the absolute max? Again, greatest cost. Is that the absolute max on this closed interval? And let's find out what that value is. So let's go to the calculator. And I'm going to go to table set. I'm going to, just a little bit of a shortcut here. I'm going to have it ask me. So now when I go to my table, I want to know when x is 4.098. Let me just double check to make sure that's right. It is, and I find out, hey, the value of this function is, and you could have done this for the other values too, 8,213.672. Again, I want to go to, each time I want to go to 3 decimal points, excuse me. So 8213.672. So these are the 3 costs at the critical values, endpoints and the critical values, and I find out that the greatest cost occurs when x equals 9. Again, the cost is greatest over the closed interval from 3 to 9 when x equals 9. And again, what do we use? The extreme value theorem. Okay, so that's it for 2041 part 3.